Hello and welcome to this lecture on shaft design and power transmission systems. What we will cover today would be the subject of designing for deflection considerations of shafts. As we know that the shafts have to be rigid and they have very strict requirements as far as the slopes or deflections that they would incur, and therefore we need to continue our discussions of stress limits, which we have satisfied so far, with another level of design to see if the diameters that we've selected for our example shaft are actually satisfactory as far as the deflection is concerned. So we will discuss this issue here, and what you'll see here is that in considerations of shaft deflections, the allowable deflections are very strict, and they depend on the component manufacturer specifications. So we have in this table showing the limits on the slopes, which are the angle of deflection, and the limit on the deflection itself. So let's talk about the deflection itself. If we have coarse gears with the pitch of less than 10 teeth per inch, then we allow deflections up to 10 mils, that is 10 thousandths of an inch. As the spur gears become finer and finer, then the allowable deflection becomes smaller and smaller. So the smallest deflection is on the order of 3 mils that is allowed at any point in a shaft that has spur gears installed on it with a pitch of greater than 20 teeth per inch, diameter inch. On the other hand, the slopes are dependent on the support system. If we have tapered rollers, for example, then the slope that is allowed, or the angle of deflection, is 5 times 10 to the minus 4 to 12 times 10 to the minus 4. For cylindrical rollers, that is 8 and 12. For deep groove balls, this is 10 and 30 times 10 to the minus 4. And for ball bearings, it's higher. Self-aligned bearings is higher, and that is up to 52 times 10 to the minus 4. So these are radians. Therefore, the angular allowable angle of deflection is, if you calculate it in degrees, then you would have to convert the radian to degrees by dividing by approximately 57. So these are extremely small slopes that are allowed under these conditions. So now the question is, how do we satisfy these strict requirements? And in order for us to do that, we need to go back to our example, which is a part of a larger case study that we will continue building up as we move on. And so far, our stress considerations have resulted in defining the diameters, as you can see here: 1 inch, 1.4, 1.625, and 2. So this is 1 diameter, second, third, 4 diameters basically that we have defined to satisfy all the stress requirements with a factor of safety of 1.5. Question is, can we actually use this to verify the deflections? So how are we going to calculate the deflections? Well, as we have seen deflection calculations, we've done that in chapter 3, and we have to now model the shaft twice, because the shaft, as you can see here, will have transverse forces and radial forces at the points where the gears are. So, and it's supported on both ends. and therefore we have to do the deflection calculations for the transverse system and the deflection calculations for the radial system, and therefore we have two planes, the XZ plane and the YZ plane, and we must do the deflections in the same way that we've learned before. So if we want to discuss it, first we have to find the shear force diagram from the reactions in the XY plane and XZ plane, and then we integrate that to get the moment distribution diagrams. These will be, since the forces are concentrated, then the shear force diagram will be constant in between different regions of the shaft, and then the bending moment diagram will give us a linear distribution of moment, and then we would say that m over EI would be equal to the second derivative of the deflection, and do a double integration. Now the problem is, in this shaft, the moment of area I is changing and the diameter is changing from position to position, so the hand integration becomes a little bit difficult. It's possible, but it's difficult and tedious because you're going to have to do it section by section, and if you're careful, it will take you a couple of pages to do that. Now what I wanted to do is go back to the idea of using a sort of a finite element software to compute the deflections of beams or shafts that have arbitrarily complex cross sections. So if you remember, we had a lecture on a MATLAB based finite element program, and we used it in a previous lecture. So now is the time to try to apply it. So let me go back and try to remind you of this idea. And the idea here is given in a beam example. Before we go back there, just a quick review of the method. The method is that you take a beam element, like a general element, as you can see here, and it has a reaction R1 and a moment M1 on one point, one end at Y1, and the reaction R2 and a moment M2 at the second point Y2. So we have a deflection Y1 and an angle of slope theta1, and at the other end we have a deflection Y2 and an angle of deflection theta2. If we do simple integration of this force system, we see that the slope is the initial value at the left point plus 1 over EI times, now you're integrating the moment and once, and you're integrating the reaction twice. So you have minus M1x plus 1/2 R1x squared. And then you do another integration, you raise x becomes x squared, and x squared becomes x cubed. And then you can put this relationship between theta and x here. If you take theta to be theta2 and y to be y2, then you have a relationship between the four terms theta1, theta2, y1, y2. These are representative of displacements, generalized displacements, and the force system, which is expressed in M1 R1 and M2 R2, and therefore we can represent equation 22 and 23 in one single equation, which is a matrix equation. So you have a stiffness matrix times the generalized displacements will give you the generalized forces here. So it's in the form of K times the displacement equals to F, where K is the stiffness matrix. So generally we have the stiffness matrix, and then we can do it element by element and sum up. So the result is, if you can see here, this example here, we have a shaft that has a moment of area of 20, and then it expands to another moment of area of 60, and it has one constant value of the elastic constant, and it has forces, one concentrated at this point with 6 newtons downward, and then a moment concentrated at the end with 5 millimeter. So for this example, we have to find the stiffness element. We have to break it down into 4 nodes, the 2 end nodes, 1 and 4. So on these 2 end nodes, we know the boundary conditions. This is 0 displacement, this is 0 displacement. And then we also know that we have a concentrated force on node 2, and we know that we have a concentrated moment on node 4, and then we know the length and the moment of area for between node 1 and 2, 2 and 3, 3 and 4. With this information, we have 3 stiffness matrices, because we have 3 elements, 1, 2, and then finally 3 here. So these are the 3 stiffness matrices that correspond to equation 24, but it's done for each of the 3 elements. And then we assemble the 3 matrices in a big 8x8, where we have the unknowns 1, 2, 3, 4 nodes, and each node has 2 unknowns or 2 displacements, y1 and theta 1. What is known is the force on that corresponds to node 2 minus 6, and the moment that corresponds to node 4 minus 50. But then we have to enforce additional displacement boundary conditions, which is y1 and theta 1 equals 0 and y4 equals 0, and those we have to introduce and solve for the corresponding forces in there. So you can put these here and then solve the system of equations to give the solution. Now this is a hand calculation. The corresponding way that we would do it is with the MATLAB code that we have now on our website. So if you look at this MATLAB code, which is very nicely done by Professor Salisbury, then you see that the beam properties are here. We have the elastic modulus, beam properties. We have for each length L1 for the element 1, and I1, which is the moment of area for beam element 1, and so on. So you have for 2 and 3, so you have 3 elements. And the node deflections are the known node deflections. For node 1 is 4, for node 4 is 0, and then the known node slopes. For node 1 we know the slope is 0. So this is like the boundary conditions. And in addition, we have a force condition. For node 2 we have minus 6, for node 4 we have minus 50. So this is basically preparing for the boundary conditions, and then we put in the K for each segment, for each element, and then assemble the K by transferring, by making a global K matrix by addition. And then we start initializing the load vector as we prepare the data for it, and incorporate the boundary conditions in the load vector, and also include any known slopes in the matrix formulation. And then finally we're ready to solve. So we solve by saying that U is equal to K over F. That's a MATLAB expression for solving the linear system of equations for the generalized displacements U. So with this way we can try to run it, and then we just kind of print. So let's try to see if we can run this code and see if we can have the results obtained for us. And as you can see, we see here that the solution, let me see if I have, yeah, so we can see here the trend already, and then we have the solution. And the solution gives us, from this code, it gives us the shear force diagram, and then it gives us the moment diagram, and then it gives us the slopes, and it gives us the deflections. And that's pretty much the results that we need for that part of the solution. So let me just close now this section, and then go back to discussion of what do we do next. In other words, what I'd like you to do is use the properties of the shaft that you've seen and prepare the data following the same example that I have here for the finite element code, and then do the calculations for the deflections and the slopes that you have. And once you do that, then you'll find that we have the following situation. So you will find that for the XY plane, the shaft is shown here. Then you have the deflection is right there, and the slopes, and the moment distribution, and the shear force distribution. So this should be your solution for the shaft. And the XZ plane would be similarly, because we have two forces opposing to one another, and while in the XY plane the two forces are actually in the same direction. So hopefully you can run the MATLAB code to recover the solutions that you can see on this page. Once we've done that, then we look at the maximum values, or at different points. Before we calculate the actual deflection and the slopes, we have to remember that we are doing things on two different planes. So we have to combine both deflections and the slopes using vector algebra, which means that, for example, the deflection will be the square root of the deflection in the XZ plane square plus the XY plane square. And the same thing happens for the slopes. So once we do that, then we see at different points. We have the left bearing slope, right bearing slope, and left gear, right gear, and then the left gear and right gear also for the deflections. So as far as the slopes are concerned, we would see that they're pretty much very small, like 0.005 radian, but the right bearing slope, you notice that it is actually greater than the allowable for a cylindrical bearing. So the right bearing is cylindrical bearing because the forces near that bearing are higher, and therefore we choose a cylindrical bearing rather than a ball bearing. So you have now a problem in the deflection that you have to correct for. So the actual practical question is, do we now reconsider redoing the calculations again and changing all of the diameters and then find the corresponding deflections? Maybe we want to do that. If we have the finite element code, we could rerun it with different input for the moments of area. We have to recompute those. Or you can actually program them yourself into the code that you have online. Another way is that to know that the deflections are inversely proportional to the moment of area, and the moment of area is proportional to the diameter to the fourth power. So a simple remedy, if you have such a result, is actually to use the old results and produce new ones by changing the diameter in the following fashion. So what we could do is say that we can adjust the diameter by saying that the new diameter is the same as the old diameter times the ratio of the deflection to the 1/4 power, because that means that the deflection is proportional to the fourth power of the diameter with a safety factor n sub d. And the same thing we could do for the slopes, to correct for the slopes. So we can do a calculation for the deflections and the calculations for the slopes, and make the corrections to find new diameters. And that's much easier than rerunning the code again, and we get decent results. So if you look at the example that we have, we want to bring back the deflection on the right bearing to 5.5 or 5 times 10 to the minus 4 radian. So the old diameter we selected was 1 inch. Apparently that wasn't sufficient, so we have to increase it by the ratio of the old slope over the desired slope with a factor of safety of 1 to the 1/4 power. So that comes out to be 1.216, which means that we have to increase the diameter by another 21.6%. And therefore we can actually apply that ratio to all the diameters that we have selected and bump them up to instead of we know now that we have 4 diameters, the ones that are supporting the bearings. We selected 1 inch. Now they have to be raised to 1.216 inches, and then the small side of the shoulders on the 2 gears will also have to be raised, and so forth. So we end up with the middle, which is the main diameter of the shaft, to be raised from 2 to 2.432 inches. And that will satisfy. Definitely we don't really need to redo stress calculations, because at this point we know that we have satisfied both the deflection calculations and the stress calculations. So at this point we have all of the ingredients that we required to satisfy the stress all over the shaft at any point, and we also satisfy the deflections and the slopes as far as bending is concerned. The last issue here is that if we have the shaft and you have a torque on the shaft, then the shaft also can be kind of rotated with a rotation angle that may be exceeding a set limit. So in other words, we have also limits on the twist angle of the shaft, and in order for us to find whether we satisfy the limit, if we have a torque, the torque is constant over a section, so we just have to find the angle that corresponds to this torque, and then if the torque it changes in another section, we have to find the additional angle that it changes, and so on, and add up all of these angles along the shaft, and that should be satisfying a certain limit. And that's basically what we have here, is that we know that the angle of deflection theta, the angle of twist theta, is TL over GJ. We've studied that. If we have several sections, each section has an angle theta I, then we add up the angles TI, LI over GJ. However, if, for instance, the torque is constant, then we can pull it out, and G is constant, then it's just a matter of summing LI over JI for the shaft to give us the total twist angle. And with that, we have completed our analysis for deflection limits and slope limits and twist angle limits for the shaft, and we're ready to move on to the next phase, which will be covered in the next lecture about vibration limits.